Hello, this is Garrett Keane. I'm continuing the series of videos on programming in Visual Basic for applications. This week we're going to look at an example called an engineering example to work out the stresses in a thick cylinder which is pressurized internally. The dimensions, the formulas are basically Lamé's formulas, and we have two formulas, one for radial stresses and one for circumferential stresses. If we look at this image here of a thick cylinder, we see we have P2 on the outside, on the inside, which represents the internal pressure inside the cylinder. We also have P1 on the outside, and this would typically be atmospheric pressure. R2 is the inner radius, R1 is the outer radius of the cylinder. And then if we just pick a section, an arbitrary element at a distance R from the center, we see it's magnified over here. Its thickness delta dr. And what we have on this little element here is a radial stress which acts along the radial direction, and we have a circumferential stress, which is also known as a hoop stress, which acts in the circumferential direction around the circumference. We see here we have the formula here. For the radial stress at any value of r, we can plug the value of r here. If you examine the formula here, you see you have P for pressure, the internal pressure. R2 is the inner radius, and that's squared upon times 1 minus R1 to be squared, that's the outer radius. And then we have small r in here. Then we have, that's all divided by R1 squared minus R2 squared. So if you look at this formula for a given cylinder of given dimensions R1 and R2, and for a given case with an internal pressure P, the only variable within this formula is the small r. This formula enables us to input a value for r, which is any value between r2 and r1, which will give us a radial position within the thick cylinder, and that will give us the radial stress at that position. And also we have the formula down here for the circumferential stress. It's a very almost identical formula. The only difference here, we have a minus in the radial formula and we have a plus here in the circumferential formula. Everything else is the same. So once again, the only variable in here is small r. Okay, if I go on to the next sheet, I have it set up here. I have this cell here is named R1, this cell here is named R2, and I'm putting in just test values of 0.2 or 200 millimeters for the outer radius, and 0.1 or 100 millimeters for the inner radius. I'm putting in a value here for 1000 newtons, which is very low compared to reality. To a lot of cases I'll actually put in 10,000, which would be more realistic. And what I'm going to do is I'm going to divide the distance between the inner radius, R2, and the outer radius into 10 intervals. So if we divide, the difference between those two is 0.2 minus 0.1, which is 0.1 of a meter or 100 millimeters, divided by 10, that gives us 0.01 of a meter or 10 millimeters. And if I come back here, what we're basically saying here is between the inner radius here and the outer radius there, I'm going to divide this into 10 equal intervals. And what we're going to do at each of those positions along those equal intervals, we're going to calculate sigma r and sigma c, the radial stress and the circumferential stress. So if we look at the formula here, we set up, first of all, we set up the radius here. I'll just make that right aligned. We set up the radius here. If you notice here in cell A10, I say that's equal to R2, so it's equal to the inner radius. I have the interval worked out here, so what I basically do, I've called this interval step. I could have called it an interval, and I basically say the radius at this next position is the R2, which is the inner radius, plus this interval here, which is 10 millimeters. So what I basically have done here is to divide the thick cylinder into 10 intervals from the inner radius to the outer radius. And if I go down through the formula, it's just a case of saying that's equal to the one above plus the step, and then all I have to do is copy this the whole way down, like so. Then what I've done is I basically have coded in Excel the formulas that we see over here. So for the radial stress, I call it sigma r. It's minus P times R2 squared. You can see that's correct. times 1 minus R1 squared divided by R squared. I should explain the small R underscore here is I've named this range here. If I select it, all the radial positions, I've named those as R underscore, which means I can use them in the formula. So when I use the formula here, it takes the first radius. When I copy down here, it takes the second radius. It takes the corresponding radius on the same row. So that's the formula there for the radial position, and I copy it down. For the radial stress, and I copy it down. And also I have the one here for the circumferential stress. You can see it's the same formula. The only difference being I have a plus in that position there, and if I come here I have a minus in that position. So I copy those two formulae down, and so when I have it here, I just get the two formulae like so, go to the right hand side, hold the button on the left mouse and drag them down. Once you get that little black dot in the left hand side, once you get the black cross, I'm able to copy it down, and it copies both formulae down. You can see what happens here is the radial stress increases from the radius, the stress. Remember, the stress at the inner radius is this stress that you're given here. That's the stress that's pushing out on the cylinder, and that goes down to a value of 0 at the outer radius where you have atmospheric pressure. So you've a pressure there, a gauge pressure there of 0. The circumferential stress is negative, and it comes from maximum value down here up to a minimum value there at the surface. It doesn't reach 0. So there's the two sets of values. Okay, I'll finish this video at this stage. The next video we're going to look at actually writing Excel functions for these two formulas here, for these two functions. Okay, thank you for listening.